Today's speaker is Roan, who's just joined us as a postdoc. He is spending part of his time as a postdoc and part of his time as our outreach coordinator. So this is the talk where he introduces himself and his research to us.
Yeah, okay. Hi, everyone. Thanks very much for coming to hear what I've got to say. Yeah, as Will said, I've just started here as a postdoc. I've been here for a few weeks now, so what I want to do really today is just give a kind of overview of the sort of stuff that I've been working on for the last few years, the kind of things that I want to work on over the next few years, and just sort of a broad overview of the sort of stuff that I'm interested in. Hopefully, some people here will also be interested in. But before I get into that, I want to just introduce myself and give you all a bit of an idea of who is this person who's standing at the front talking to you. It looks kind of vaguely familiar. So I grew up here in Kent in the southeast of England. Kent is a wonderful place and is interesting from an astronomical perspective, I think, because it has been shown to violate the cosmological principle by being conclusively proved to be the center of the universe. It's a cosmology joke I won't do anymore, I promise. I did my undergraduate at Durham University, which is a very, very nice city, Durham. If any of you have been there, you'll know that. It is home to this building, Durham Cathedral, which is where some of the scenes in Hogwarts were shot for the Harry Potter films. And then I moved to the University of Nottingham, where I did my PhD. Nottingham was also a lovely city, and I would recommend anyone go there to visit. And it is home to this building, which is called Wallerton Hall, which was used as Wayne Manor in the Dark Knight films. And then a few weeks ago, I moved here to Waterloo. I don't know if Waterloo has any Hollywood connections. If it does, then I would love to hear them.
I remember there was the Shrank Everyone at Perimeter. There was a movie where everyone got shrunk. It was filmed at Perimeter. Anybody remember that? No, it's a more recent one. Everyone got shrunk to kind of, but Matt Damon, I think, was on it. Downsizing, that's what downsizing, yes. That was
Matt Damon in Perimeter sounds excellent. Definitely gonna watch that. I believe I've not seen that. But anyway, I'm not going to talk about me anymore. I'm going to talk about science because it's more interesting. So my research really centers around galaxy clusters. This is what I'm really interested in. As I'm sure we all know, galaxy clusters are these groups of hundreds of thousands of galaxies held together in these big dark matter halos, typically of masses 10 to the 14 or 10 to the 15 solar masses. I'm interested in clusters for a variety of different reasons, but one of the big ones is from a galaxy evolution perspective. So galaxy clusters play a really important role in galaxy evolution because the evolution and the properties of galaxies are strongly dependent on their environment, their local density in which we find them in the universe. If we look, so this is a plot that I'm sure lots of people are familiar with. If we look down this end, we're looking at less dense regions of the universe, the cosmic field, and we find loads of these late type spiral galaxies. And then as we move to increasingly dense parts of the universe through intermediate environments like groups and filaments into clusters, which are the densest regions of the universe, we find fewer of these spiral galaxies and more of these early type elliptical and lenticular galaxies. And this is for a variety of different reasons, but essentially the evolutionary processes that a galaxy goes through differ depending on what density its local environment has, whether it's in a field or a cluster. The picture's a little bit more complicated than this because galaxies don't just live in one environment for their entire life. Galaxies can move between different density environments. Clusters, for example, grow by accreting galaxies from the field. So these galaxies start from these less dense parts of the universe and then move into these denser regions of the universe where their morphology can change, but they can also experience things like removal of their gas, stopping of their star formation, all of these things which are dependent on the local environment of a galaxy. This is why, so I've mentioned pre-processing at the bottom here. This is essentially where this comes into it. So pre-processing is when galaxies evolve before reaching it. So before entering a cluster, galaxies can pass through various different environments. So a galaxy might enter a cluster as a member of a galaxy group or through a cosmic filament, And these are things that will influence the evolution of a galaxy before it enters the cluster. We call this pre-processing. And then finally, this isn't just a one-directional process either, because as I'll talk about in a little bit, galaxies that were previously in an environment can leave that environment and then re-enter it at some time in the future. So it's a little bit of a mess, and trying to figure out exactly how different environments influence different parts of galaxy evolution is not a completely straightforward question. Now, all of these processes, this build-up of clusters and the evolution of galaxies, takes place over billions of years, which is why cosmological simulations are so useful. These allow us to take a galaxy cluster and look at how it's evolved over billions of years, rather than staring at the sky for a billion years, which nobody really wants to do. And simulations are what my research is built around. So I primarily use a set of simulations called the 300 suite of simulations. This is a set of 324 hydrodynamical simulations of large galaxy clusters. These clusters are simulated out to several times their virial radius. So that means we can look at not just how the cluster itself forms and grows over time, but also what happens in the outskirts of these clusters, what happens to things that are about to be accreted into these clusters, and how the galaxies that join this cluster population have changed over the billions of years before they actually reach the cluster itself. What I've got here is an example of one of the clusters from this suite of simulations. This is one of the simulated clusters at redshift 0. And this is kind of the picture we might have if we were to go out and observationally look at this kind of cluster. We can see this circle here is R200 of the cluster. This is its kind of characteristic radius. And each of these blue points represent galaxies that are either inside or in the immediate vicinity of them. And so if we were to look at a cluster, this is the kind of thing we might see. But because this is taken from a simulation, we don't just have the view of what this cluster looks like now. We can look at where all of the galaxies in this cluster have been in their past, where they've come from, what paths they've taken to approach the cluster. And what I've tried to do here is highlight 3 different classes of galaxies that we get in and around clusters. In the top left here, this pink cross is what we call infalling galaxies. So these are galaxies that are on their way to a cluster. They're approaching a cluster for the first time, but they've not actually entered the cluster yet. So these are ones that may have been influenced by things like pre-processing, may have just fallen in from the cosmic field, but have not yet got to the galaxy cluster that they're being influenced. Secondly, we've got this green circle, which shows an example of a bound cluster member, the kind of satellite galaxies that make up the general cluster population. This is something that is inside of the cluster radius, has been for some time, it's fallen and it's now on some bound orbit around the cluster center. And then finally, down here in the corner, this red star, we have what we call backsplash galaxies. And these are galaxies that when we look at them now, if we look at a cluster redshift 0 or redshift approximately 0, we might see these galaxies outside of the cluster. We might see them in the cluster outskirts, in the region where we find these infalling galaxies. But clearly what we can see is that this backsplash galaxy has had a very different history because it's fallen into the cluster, passed through the cluster center, and has come back out again. It's now on some second infall towards the cluster. Now, what that means is that backsplash galaxies effectively act as a contaminant when we're looking at the outskirts of clusters, because naively, we might look at the outskirts of a cluster and think these are infalling galaxies that have just been influenced by pre-processing effects. But actually, this backsplash galaxy here will have experienced strong tidal forces, strong stripping of its gas through previously passing through the cluster. And so these effects might appear to be due to pre-processing, but in fact, they are just due to the cluster itself. And so these backsplash galaxies kind of contaminate our studies of infalling galaxies and what happens to galaxies before they reach a cluster. In order to try and reduce this contamination, the question we need to ask ourselves is how common are these backsplash galaxies? How much of a problem is this contamination? The problem with backsplash galaxies is obviously within observations, they're quite difficult to pick out because we only get this one snapshot, but within simulations, we can easily find them and we'll see how much of a problem actually are they in this context. What I found from my work is that if you look in the immediate outskirts of a cluster, roughly half the galaxies there. So if you look between R200 and twice R200, about half the galaxies there are backsplash galaxies. So this is, quite a major effect of half the galaxies that might appear to be infalling galaxies are actually things that have been through the cluster before. What's interesting about this, though, is that this fraction isn't the same for all clusters. We found that dynamically relaxed clusters have more of these backsplash galaxies around them than dynamically unrelaxed clusters. These relaxed clusters are going to be fairly isolated. They won't have experienced any major mergers. They'll have loads of these backsplash galaxies in their outskirts. Whereas a more disturbed cluster that is accreting lots of material will have far fewer of them, or a much smaller fraction of these backsplash galaxies. This is really useful because, as I said, backsplash galaxies are hard to find observationally, but we can observationally measure the dynamical state of a cluster. There are various different proxies for it. We can look at a cluster and we can tell if it's a relaxed or an unrelaxed one, which means we can make a prediction of how much this contamination is going to matter. Is this cluster going to be 70% backsplash galaxies in its outskirts or 20%? So this is an example of how simulations can be really useful in that when we apply what we find from them to observational astronomy, they can let us imply more info, they can help us make inferences that we wouldn't otherwise be able to make. So after this, I wanted to go a little bit further and try and figure out basically what else is going on in the cluster outskirts. Yes.
So, I mean, what you're suggesting there is like if you have like some very relaxed clusters, which have 90% or like 85% of the galaxies are backsplash. But that just seems weird.
It does seem weird.
Yeah.
This is why they're important to consider, because you wouldn't expect that 85% of the galaxies around one of these clusters have previously been.
Like, is it an FW, the distribution of galaxies? Because, yeah.
It depends on the cluster. So relaxed clusters, I'll make sure I get this the right way around. For relaxed clusters, these tend to be, it's a fairly flat distribution out to about 1.5 to 2 R, about 2 R200s. And then it drops off quite sharply. You get very few beyond that. It's not an FW. So I'm talking about the fraction of backsplash galaxies. So the fraction is fairly constant out to about 2 R200, then drops off quite sharply. But unrelaxed clusters, there are a lot more clustered towards the center. So most of these backsplash galaxies are just outside of R2.
But that's the thing that, I mean, in terms of mass, the fraction of mass in that range, and I guess you shouldn't really use an FW outside R200. So it just seems that you don't have that much mass that range compared to the mass inside R200. You said 90% of galaxies are there.
So this is when you look at galaxies between R200 and if you take an annulus around the cluster, then
90% is, yeah, so it's between R200 and R200 divided by everything within.
Divided by all of the galaxies in that ring.
90% of the galaxies in the ring are backsplash. The other 10% are.
Oh, okay. So I should say I was thinking of everything in the whole. Okay.
No. So
within the ring. Right?
Yeah. So if you look at all of the galaxies in that ring, yeah, 90% of them are backsplash.
Things are going out versus. Okay, so the rest of them haven't been inside the ring already.
Yes, exactly. So if you look outside of R200, 10% of them are falling in for the first time, 90% of them have previously been inside the first time.
Okay. Yeah, thanks.
So a related question, since we stopped you, so how much of that is dependent on the fact that you're choosing R200, which is kind of an arbitrary number. So for example, if you chose the virial radius, which is also arbitrary, like an R100, farther out, we're really asking the question, how many of these things have been within the virialized part of the cluster?
Yeah, so you get, I mean, the numbers do move around, but it's the same kind of general trends. So like I said, for unrelaxed clusters, these backsplash galaxies tend to be distributed just outside of R200. So if you use a bigger radius, then you have you have almost no backsplash galaxies in an unrelaxed cluster, whereas a relaxed one, you will still get some because they're spread further out. Similarly, if you use a smaller radius, most of these backsplash galaxies, you don't get many on these kind of grazing orbits that like just dip within R200 and then come back out again. most of them are on quite radial orbits, and so they'll pass within 0.5 R200 of the cluster center. So if you use a slightly smaller radius, you're not missing any of these backsplash galaxies because they've all gone right through the middle.
Yeah, I guess it's just sort of in the physical interpretation of what backsplash means. I mean, if you chose, a small radius like 0.3 R200, everything out there would be backsplash just because everything is just orbiting around. It doesn't mean anything. They're all materializing back to the cluster.
Yeah.
Right. And so R200 is kind of an arbitrarily small radius sense. So
Yeah. Just
measuring the fact that the materialized cluster is larger than R200 and things are orbiting around. That's kind of a different.
I suppose so. But if you were, if you're interested in things that are now beyond the cluster influence, you could look at only backsplash galaxies outside of 1.5 R200, say, and those would all still be things that have punched right. You would still be getting the same galaxies that we're talking about here. It would be a subset of them. So all of these ones are ones that have punched right through the middle of the cluster. Okay, so that's kind of all I want to say about this, really, because I wanted to kind of, after this, I sort of wanted to move a bit more generally and talk, well, look at what else is going on in the outskirts of these clusters. How else can we constrain the environmental histories of these galaxies? What I've got here is an image. This is one of the clusters from the 300 set of simulations. This is a plot of the cluster itself in the middle, and then the cosmic filaments that are coming out from the center of this cluster. If we extended these out, this would kind of join into the whole cosmic web. This is a plot made by Lee Kuchner, who's a postdoc at Nottingham, who is excellent at making these kind of things. But if we also look on here, what we've got is these smaller structures, smaller than the cluster itself, and these are galaxy groups. And these play an important role in galaxy evolution and the build-up of galaxies in the cluster. These typically contain tens of galaxies or so, and are a way of feeding large amounts of galaxies into a cluster. I wanted to look at what happens to these groups as they approach a cluster and how the groups themselves are influenced by falling into a galaxy cluster, and also how this might affect the galaxies within these groups as well. What kind of processes might they go through? I've just got a kind of schematic here that hopefully will set us up for the next few slides. So what I'm showing here is a galaxy group that is falling into a cluster. So this is the cluster halo here, this big grey circle with its characteristic radius. And then our galaxy group is this smaller yellow circle that has just fallen into R200. It also has a halo with a radius, and then these blue crosses are the galaxies that are a member of this group. We define our galaxy groups as galaxies that are gravitationally bound to this halo at the moment when it enters the cluster, gravitationally bound to the group halo, but also with an outer limit of 2.5 R200. So don't have something that is a huge distance away that is bound to it. These have to be things fairly close by to the group and bound. What that means is that we have this group of bound galaxies that are all falling into the cluster together. Then for each of these galaxies, we describe them by these two quantities, R, which is the distance of the galaxy from the center of its host group, and the speed at which this galaxy is moving, again, relative to the group that it's bound to. And so by looking at how these two things are distributed, these distances and speeds of the galaxies, we can build up basically a phase space of the dynamics of this group. What do the dynamics of this group look like? How are the positions and speeds of these galaxies distributed within this group? If we do this for many groups falling into many clusters and stack it together, then we end up with this plot here on the right, which basically shows how these two quantities are distributed for these galaxies. On the horizontal axis here, we've got the distance of galaxies from the center of their group at the moment when the group enters the cluster. On the vertical axis is the speed at which these galaxies are, again, relative to their host group. So on the left here, we've got galaxies that are near the middle of the group. On the right, we've got galaxies on the group outskirts. I've just got a schematic up here. reminding us that this is when the group is first falling into a cluster. But this is all well and good, and it shows us sort of where within this phase space these galaxies are. This red line as well is the criterion that we use for being approximately gravitationally bound with this cut at 2.5. Things lying below this red line are bound in this group. And this shows us how these galaxies' speeds and positions are distributed. But this isn't groundbreaking. You know, there's other papers that have done this before. I've got an example of one from a paper from a few years ago there. Well, that was using dark matter only simulations, which makes it correct. Sorry. So this is kind of where we started off, but what I wanted to look at is how do the dynamics of these groups change as they pass through a cluster? How does this phase space evolve over time? And the way that we can do that is by taking this plot and basically looking at these galaxies that are bound to the group. How do they move around in this phase space? How do their positions and their speeds change? How do they move around in this figure as the group passes through a cluster? The way that we do that is by making plots like this, which obviously there's a lot going on, so I'll take a couple of minutes to talk about this. This is showing as a group falls from the outskirts of the cluster towards the cluster center, how do the galaxies that were bound to this group move around this space? This is all galaxies that started off bound to the group, started off below this red line. And this is showing us the ones in different regions of this phase space, how are they moving? So there's some stuff up here which are things that have moved above this red line have become unbound from the group. And they are clearly still moving around in this phase space as well. Darker colours here represent just things that are moving around these plots more quickly. And again, I want to stress that this is positions and speeds relative to the group, not relative to the cluster. So what we see here, clearly, there's kind of a fairly bulk behaviour. That for the most part, things are moving upwards. Now, what that means is that the distance from these galaxies to their host group, that is not changing very much. What's changing is the speeds at which these galaxies are moving. That tells us as this group is approaching the center of the cluster, as it's approaching the pericenter of its orbit, these galaxies are getting this big kick in kinetic energy, this big increase over a pretty short period of time in their speeds. This kick is fast enough that a lot of them move above this red line and so become unbound from the group that they were previously bound to. But we're also finding that at least at this time, the positions of these galaxies haven't moved very much. Although they've had this fairly instantaneous kick in their energy, these galaxies have not moved further away from the group. These groups are still fairly coherent. All of the galaxies are moving together at this moment. Yeah, please.
On the y-axis, you're plotting V over that in fall.
Yes.
So does that mean that the denominator is constant as the group is moving in?
Yeah.
So it's not. I mean, so is that not just reflecting that the whole group then is, speed as it accelerates towards the cluster?
No, because these are the speeds relative to the group halo. So if you had the group halo and a galaxy were moving at the same speed, this V would be 0.
Okay, so it's the velocity difference relative to the group halo.
Yes, relative to the group halo, not relative to the cluster. This is just showing groups that are approaching. Okay.
What is this here?
It's what is it? It's just some characteristic velocity. It's the circular velocity of something orbiting at.
The circular velocity within the cluster halo or within the group halo?
No, so again, this is all relative to the group. So this is for something, I think something orbiting at R200s in the group's NFW profile. What would its circular velocity be?
This is just a snapshot, right? So if you let it evolve with time, really there's going to be an adjustment. Right?
It's funny you say that. So I think this is what you're getting at. If we look at these same groups a little while later, after they've passed pericenter, we're not still seeing this same behavior. So whereas before we saw things moving upwards on this, which was that kick in velocity they got, what we see a short while later as these groups have passed pericenter and are receding from the cluster, is obviously very different. For the most part, what we're seeing is kind of movement left to right. The speeds of these things aren't changing around that much, but what we're getting is this big increase in the distance of these galaxies to their group halo. This kind of tells us that the evolution of these groups is taking place in two phases, right? First of all, they get this big kick in energy that moves galaxies upwards. They move above this red line. A whole bunch of them become unbound. And then a short while later, maybe half a gig year later or so, after the group has passed pericenter, these galaxies move left to right. That increase in energy manifests itself and they fly away to higher distance. The distance of these galaxies from their host group increases. The groups get scattered to high distances. It's a little bit kind of abstract talking about it in these terms. So I wanted to show an example of one group and this happening to a particular galaxy group that is falling into a cluster and passing through the cluster potential. So on the left here, we've got this same phase space diagram showing all of the galaxies that are members of this group. How are they distributed in terms of their positions and their speeds when the group enters a cluster? And then on the right, what I've got is the cluster halo and the group, the positions in real space of all of the members in this group. And so what we can do is we can watch as this group falls in and passes through the cluster. All of the galaxies in this group move through this way, and we can see how they move, how their movement in the phase space corresponds. So as the group sort of falls into the cluster, first of all, we see this first phase that I was talking about, where the galaxies move upwards like this. They get that big kick in their speeds. A bunch of them move above this black line, so they become unbound. But if we look here, the group itself is still fairly coherent. All these galaxies are still pretty nearby to each other. But if we look a little while later, as this group sort of recedes from the cluster center, we move into this second period where the galaxies, where the galaxies move from left to right on this plot. Their distances from their host group increase. And indeed, when we look here, we see that this group has been scattered up. All of its galaxies have been thrown away to high distances, particularly the ones that moved above this black line that became unbound from the group. They've then just been scattered. And by the time the group has made one passage through the cluster, it doesn't even look like a group anymore. If you looked at this, you would never identify this as a galaxy group.
What happened to the halo?
The halo is still, so this thick black line is following the group halo itself.
The halo is still coherent, or is it puffed out now? It's now lost mass, right?
Yeah, it's lost a bunch of mass. So this passage through the middle, I think, strips about 2/3 of the halo's mass in our simulations.
And that just merges with the overall.
For the most part, it just merges into the cluster halo. So it's just been tidally stripped by the cluster. So I suppose that effectively that's analogous to what's going on here, right? The halo itself is pulled away and these galaxies are also stripped away at the same time. Now, what we find is that this isn't an isolated incident. This happens to almost every cluster, almost every group that falls into a galaxy cluster. Essentially, the conclusion is groups do not survive when they pass through a cluster potential. And this is really useful because what this tells us is that if we look at a galaxy cluster and we see a group nearby to it or just inside of it, this is not something that's been hanging around the cluster for a few billion years, because as soon as a group approaches a cluster, it immediately gets stripped and pulled apart, all of its galaxies flung off to high distances. And so any groups that we see near to a cluster are things that have approached this cluster really, really recently. Now, I want to kind of, try and think about why should we care about any of this. And that is because, as I mentioned right at the beginning, the properties and the evolution of galaxies are linked to their environment. And this is not just the environment that we see them in now, this is all of the past environments they've gone through as well. These all influence what a galaxy looks like when we observe them today. Whether that's passing through a group or previously passing through a cluster like a backsplash galaxies. These all influence the way that a galaxy evolves.
Go back for just a second.
Yes.
Usually, when we see movies of things being tidally stripped, there's the core that's there, and then the rest of the stuff is pulled out in a stream, right? Leads and lags the orbit. But usually those objects seem to follow the same orbit, just ahead or behind the main halo, the main part of the halo, like if you look at movies of satellite stripping. So I would have thought groups would be similar to that, except that now it's galaxies instead of stars or dark matter particles which are being stripped. But you're implying on the previous slide that some of these are sort of thrown off to infinity, which doesn't sound like the same picture. So is that correct, or?
I mean, not to infinity. These are all things that.
But they don't. It's not a simple. Doesn't look like a simple case where they're just leading or lagging the same orbit that you normally see when other movies of stripping of other objects.
Yeah.
I don't know what's
That's the mean, the black is the mean,
yeah the
and the relative velocity.
the brown, the orange, and the yellowish. I don't know where they're going to go next. Are they just going to go out a little bit and come back?
Next slide, but.
Come back, or are they just going to go off?
This is
somewhere
Redshift 0,
else?
I'm afraid. This is all we got.
I mean, I agree with Mike. I mean, with the leading lagging thing, effectively strip sort of along the orbits of the black line, right? So
Yeah.
there'd be some behind it and some ahead of it, but they're sort of being angled.
I see what you're saying. I suppose the first thing I haven't got an answer for you. The first thing that comes to my mind is maybe the fact that these are discrete objects. They have very different initial conditions, right? These things had different speeds when they fell into the cluster. They didn't all fall in on the same paths. They can't really be considered as just a cloud. Some of them fell in, although the group fell into the cluster. Some of these galaxies in this group would have been kind of orbiting around like this, and some of them would have been orbiting this way. So they would have fallen in with slightly different trajectories, even though they all fell in as a bound group.
As it'd be interesting to see the dark matter particles associated with that group as well, to see if they have a different pattern. It just happens that these tracers are tracing different region of phase space.
Yeah.
But also maybe post, and probably the tidal forces were maximum when it was running through. So now it's at the edge. Is that right? And so you've got slower stars and faster ones, and so the slower ones will be kind of turning around. Reasonable. And then the faster ones are shooting off, and they're starting to turn.
Yeah, that's the question. Are they going to turn around? Are they going to turn around or not and pull back on the same orbit, a little bit lagging?
Yeah, it looks kind of like they are, but gotta go to the next slide.
I mean, I've got an awful lot more to say about this. I'm happy to have a chat about it. Yeah, I mean, so these things, I mean, these are backsplash galaxies, what we're looking at here, right? They fit our definition, which for the most part will go out to maybe twice up 200 on a good day, and then they'll fall back in towards the cluster. So these aren't things being scattered off to ridiculous distances. Yeah, it would be interesting to even just look at a few examples like this and kind of overplot this with the particles of the dark matter halo and see how much do these trace the kind of tidal stripping you get particles from that.
Time galaxies, like do you quantify them every time step? The center of mass is associated with the time step, or
Yeah. So there's a whole pipeline of running a halo finder on each of the time steps of the simulation, so that finds structures that have got a certain stellar mass and a certain dark matter mass and a certain number of particles that are all bound together, and then we call that a galaxy. Do that in every snapshot, and then string them together by basically seeing there are two structures in subsequent snapshots that share most of their particles. They're most of the galaxies. Any more? Essentially, what I want to take away from this is that this is another example of how we can use simulations to interpret our observations differently. This has told us that the vast majority, greater than 95% of groups that fall into a cluster don't survive a single passage through the cluster, immediately get stripped apart. And so this tells us that if we go out and we look at some substructures or galaxy groups nearby to a cluster, we know that these are things approaching the cluster for the first time. Otherwise, they would have been torn apart. I want to do a kind of a worked example here to really drive my point home. So this is, again, one of our simulated clusters, and this is shown in dark matter on the left, gas in the middle, and all of these bound structures that we identify as galaxies on the right here. And so I suppose mostly this one on the right, this might be how we could go out and see a cluster. You kind of see the gas there, but not really in the same resolution as this. And so we might go out and see this cluster and be trying to figure out where the galaxies in it have come from and what environments they've gone through in the past. And so we can use the kind of things that I've talked about today. Like we want to know how many backsplash galaxies there are in this annular series between R200 and twice R200. The first thing we can do is we can ask ourselves, what kind of cluster is this? And this is a dynamically relaxed cluster. You can sort of see it's quite centrally concentrated. It's not got any big mergers going on. It's fairly symmetric. And so that tells us relaxed clusters, loads of backsplash galaxies around them. We would already expect there to be a lot of backsplash in the outskirts of this. But if we look down here in the bottom left corner, then we can see a few slightly larger structures. And these are galaxy groups that are around this cluster. These are things that we know are almost certainly on their first inflow. So these things are very unlikely to contain any backsplash galaxies. These are things that are falling in pristinely to the cluster, having not experienced that kind of environment before. And so we would expect there to be very few backsplash galaxies associated with these structures down in the bottom left corner. And because these are simulations, we can check how this fits with what we actually see. If we colour in all of the backsplash galaxies in red here, we see that there are loads of these backsplash galaxies around this cluster. I think it's about 70% of the galaxies in the outskirts of this cluster are backsplash. But if we look down in the corner here, where we've got these informing groups, there's a much smaller fraction. There's very few backsplash galaxies down here compared to the number of informing galaxies. And so this kind of thing allows us to not only make predictions about how much of this contamination of these infill regions there is by backsplash, but also try and split up the cluster into different regions and go at least some way to saying there's more contamination here than there is here.
Also, it's interesting that if you look at the dark matter, you see the cluster is not purely symmetric, but it has like an axis.
Yes.
Yeah, so backsplash galaxies are along that axis.
Yeah, so this cluster has two big filaments. There's one coming out the bottom, one coming out the top here. That is something that I've done a little bit of work on. I want to do more on, is seeing, is there any link between these backsplash galaxies and these big cosmic filaments? Earlier, I mentioned earlier, who did the nice plot of the filaments. I worked on her with a paper, and she's got some kind of preliminary results on that in there. I want to kind of get down into it at some point.
What happens to the atmospheric gas? Groups coming in, does that get stripped off and left in?
You mean in the kind of the galaxies or in the group itself?
The group itself has its own intergrouping. That just gets stripped out and gets absorbed.
Yeah, almost entirely.
The backsplash galaxies are pretty much. Yeah, so I guess you don't know.
Yeah, I mean, so what we find from these simulations is the backsplash galaxies have essentially no gas in them at all. I'm always a little bit skeptical of trusting things like round pressure stripping in hydrodynamical simulations. But we've done some analysis of backsplash galaxies using some semi-analytic models, and we do also find this, that they have little to no gas in them at all.
So things that you identify, real things on the side, they tend to be red, and backsplash galaxies.
Again, they are within these hydro simulations. it was something we took a very quick look at with the semi-analytic models. And again, it does appear that that's the case. They have small, very little gas in them, so very low star formation rates. But that is something that I'm planning on working on. I'm working with some people who run these semi-analytic models, and they're interested in looking at that as well. So that's kind of work in progress.
Hydrosims and 300 the same physics as anything else like Eagle, or are they their own?
They all
Subscription.
so the 300 is run. There's 324 clusters, but each of them is run several times. They're run with, I think, 4 different physics models. So there's a couple of versions of Gadget. There's one run with Gizmo. I mean, Gadget is kind of more along the lines of Eagle, but tuned differently because it's a much bigger volumes. But as I say, there's a few I can't remember all off the top of my head now, but it's run with several different codes, which hopefully makes these things a little bit more robust. Yeah, and different. So, for example, so actually, what I've got here is just using the Gadget X runs of the simulations because the other ones are quite recent developments. But for example, Gadget X, the black hole masses are a little bit skewy in it. So that's something that's been kind of fixed and run differently in some of the other ones of these simulations. Okay, that is. There we are. That's pretty much where I am at the moment. So I've sort of covered a little bit of this just now, but these are just a few things that I'm interested in at the moment and that I'm planning on working on. I want to link backsplash galaxies with machine learning. So everything I've talked about has been kind of statistical ways of doing this. How can we predict the contamination around the cluster? Say cluster is 70% backsplash galaxies. What I want to do is to train a model in order to be able to identify individual galaxies. This one is backsplash, this one is not. And that would allow us to remove these galaxies and not just quantify this contamination, but actually remove it altogether and get a pure sample of infalling galaxies or a sample of backsplash. Okay. I want to look at different processes like mergers and stripping that happen in different regions of groups. This sort of links in with what we're saying about how the gas in the groups and the groups themselves is also influenced. And dynamic states of clusters. I'm currently in the very early stages of a project looking at simulation-based and observational measures of dynamical state and how well these work with each other. I've put splashback radius down here because it's something I have a passing interest in. But this is sort of very early stages project, but something I'm quite interested in. I'm going to finish up in a moment. I've got just sort of summarizing my talk in 2 sentences here, which is that cluster properties tell us how many galaxies have previously been inside the cluster, and the galaxy groups have not been inside the cluster in the past. But before I finish off, I just want to talk about something else for a moment, which is science outreach, which, as Will mentioned, is something I'm going to be spending a fair bit of my time doing here. Science outreach is really good, and everyone should do it. I did quite a bit during my PhD, and I'm going to be spending about half my time here trying to do some outreach with the WCA. There's already a few really cool things going on here, but I want more. Here's just a few things I'm involved with. These 2 on the left are 2 sort of science communication things online that are both really fun, and if you want to get involved in either of them, then just let me know. On the right here is a picture of a couple of pictures of the inflatable planetarium that we had in Nottingham that I used to work with, which was really cool. And we've got one coming to the WCA, hopefully at the end of this month, which I'm looking forward to having a play around with because it's way better than the one that we had when I did my PhD. This is a picture of, this is a very staged photo of me talking about outreach to people. I like this picture because it's a stage photo of me talking about a stage photo of me working. And I'm hoping after we finish today, someone can take a picture of me with this, that I have a stage photo of me talking about a stage photo of me talking about a stage photo of me working.
Come on, the other slide.
Okay,
Yeah, perfect. I can use that in my next talk.
We gotta
There are many good reasons to do outreach. I won't spend too long on this. First of all, it's really fun. It's nice hearing people tell you that they like astronomy. It's nice hearing people's questions about it. It's nice people telling you you've got the best job in the world because it makes you feel good about yourself. It's also your social responsibility to do outreach, so you should be doing some. So that's fine, thank you. We're very fortunate that we have very, very fun jobs. And we're in a fairly unique position where we can go out and tell people, look at how fun science is. If you be a scientist, you can have as much fun as me. Which not only encourages people to, particularly young people, not only encourages them to pursue a career in astronomy, but can encourage people to pursue a career in any of the other sciences. I think we all agree that the more people want a career in science, the better. Finally, this is one more for the students in the room. You won't get a job out of it. Part of the reason I'm here is because I did some outreach and I'm being paid to carry on doing it. It's a great thing to put on your CV and to talk to people about. It shows that you're a person who actually cares about the wider implications of science. It shows that you're not a social oddball who just sits around writing code all day. We're picking out the social oddballs all of a sudden. It's very good, and everyone should get involved with it. But anyway, that's pretty much all I've got to talk about. I'll put my conclusions back up here. Here's a couple of archive numbers. If I could summarize all my work in one sentence, it's basically that simulations are really useful in helping us interpret observational astronomy more deeply. And in particular, in the context of what I do, this can tell us more about the cosmic environment and the environmental histories. I'll stop there and I'll take any questions anyone has. Thank you.
Any more questions? Any questions online?
Yeah, I have a question.
Hello?
Can you hear me?
Yeah.
Hi. I was just wondering, are the simulations at a point where they are making predictions for differences in how the star formation histories in different galaxies, like backsplash versus not backsplash? Like, can you see if there's any differences in how the star formation histories go depending on, their orbit throughout the cluster?
Yeah, so I suppose it depends on the approach you want to take. So you can pick this out of hydrodynamical simulations. I'm a little bit skeptical of that kind of thing, particularly with these simulations. The resolution of these isn't great, right? You can't pick out any real details of a galaxy. And so these kind of simulations are great for looking at this sort of structure and cluster substructure. I'd be a bit hesitant to use these simulations for looking at things like star formation histories in any real detail. But this is something that we want to look at using semi-analytic models as well. Although again, you need to be sort of very careful with what you feed in and what you read out of those. But it's something that I want to have a little bit more of a look at.
Okay, thanks.
All right, thank you.
Okay, any more questions? Mike?
Right at the beginning, you had some measures of relaxedness, but maybe I missed it. How would you implement those observationally? Like, what are they and how well do they work observationally compared to what you can see in 3D, for example?
Yeah, so the measures, the measure that we've got of dynamical state is a pretty simulations focused one. So it's one number that basically combines three measures, which is the center of mass offsets, the offset of the BCG from the center of mass of the cluster. It's the amount of substructure that we have, so the amount of mass in subhalos, because relaxed clusters are more centrally concentrated. And it's also this quantity, the virial ratio, which is basically a measure of how close to being virialized the cluster is. that is something that is
Just like the ratio of kinetic to potential energy.
basically, yeah, I can't remember exactly how it's defined. That's obviously a kind of a tough thing to measure observationally. Center of mass offset it can be measured observationally, but also is hugely dependent on projection effects. If you've got a center of mass that's offset in the line of sight, you're not going to see anything. Subhalo mass fraction is something that I've seen used as a measure of dynamical state, because I mean you can use X-ray measurements to pick that out to some extent. It's a tough one. I mean, even so, substructure fraction you can sort of get even just from richness of a cluster, because if you've got a cluster that is dominated by a really bright BCG and then lots of faint galaxies, then that is going to be more relaxed. Whereas a very rich cluster with loads of bright galaxies in it is going to have more substructure, and so it's likely to be a less relaxed cluster. So there are kind of analogs. You couldn't exactly what we use, you couldn't measure observationally, but these things are all correlated with each other. Each of the three measures that we use all individually correlate with the mass flash fraction as well.
Okay, any more questions in the room? No, any more questions online? No? Okay, let's thank Rowan again. Bye.